Section 25 of Gray's Anatomy, Part 2. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recorded by Laurie Ann Walden. Anatomy of the Human Body by Henry Gray, Part 2. Mechanics of Muscle. In studying the mechanical action of muscles, the individual muscle cannot always be treated as a single unit, since different parts of the same muscle may have entirely different actions, as with the pectoralis major, the deltoid, and the trapezius, where the nerve impulses control and stimulate different portions of the muscle in succession or at different times. Most muscles are, however, in a mechanical sense, units. But in either case, the muscle fibers constitute the elementary motor elements. The direction of the muscle pull. In those muscles where the fibers always run in a straight line from origin to insertion in all positions of the joint, a straight line joining the middle of the surface of origin with the middle of the insertion surface will give the direction of the pull. If, however, the muscle or its tendon is bent out of a straight line by a bony process or ligament so that it runs over a pulley-like arrangement, the direction of the muscle pull is naturally bent out of line. The direction of the pull in such cases is from the middle point of insertion to the middle point of the pulley where the muscle or tendon is bent. Muscles, or tendons of muscles, which pass over more than one joint, and pass through more than one pulley, may be resolved, so far as the direction of the pull is concerned, into two or more units or single joint muscles. The tendons of the flexor profundus digitorum, for example, pass through several pulleys formed by fibrous sheaths. The direction of the pull is different for each joint, and varies for each joint according to the position of the bones. The direction is determined in each case, however, by a straight line between the centers of the pulleys on either side of the joint. The direction of the pull in any of the segments would not be altered by any change in the position or origin of the muscle belly above the proximal pulley. The action of the muscle pull on the tendon. Where the muscle fibers are parallel, or nearly parallel, to the direction of the tendon, the entire strength of the muscle contraction acts in the direction of the tendon. In pinnate muscles, however, only a portion of the strength of contraction is efficient in the direction of the tendon, since a portion of the pull would tend to draw the tendon to one side. This is mostly annulled by pressure of surrounding parts. In bipinnate muscles, this lateral pull is counterbalanced. If, for example, the muscle fibers are inserted into the tendon at an angle of 60 degrees, it is easy to determine by the parallelogram of forces that the strength of the pull along the direction of the tendon is equal to 1/2 the muscle pull. T equals tendon, M equals strength and direction of muscle pull, small t equals component acting in the direction of the tendon, phi equals angle of insertion of muscle fibers into tendon. Cosine phi equals small t divided by m, cosine angle 60 degrees equals 0.5. 0.5 equals small t over m, t equals 1/2 m. If phi equals 72 degrees 30 minutes, cosine equals 1/3. If phi equals 41 degrees 20 minutes, cosine equals 3/4. If phi equals 90 degrees, cosine equals 0. If phi equals 0 degrees, cosine equals 1. The more acute the angle phi, that is, the smaller the angle, the greater the component acting in the direction of the tendon pull. At 41 degrees 20 minutes, 3/4 of the pull would be exerted in the direction of the tendon, and at 0 degrees the entire strength. On the other hand, the greater the angle, the smaller the tendon component. At 72 degrees 30 minutes, 1/3 the muscle strength would act in the direction of the tendon, and at 90 degrees the tendon component would be nil. The strength of muscles. The strength of a muscle depends upon the number of fibers in what is known as the physiological cross-section. That is, a section which passes through practically all of the fibers. In a muscle with parallel or nearly parallel fibers which have the same direction as the tendon, this corresponds to the anatomical cross-section. But in unipinnate and bipinnate muscles, the physiological cross-section may be nearly at right angles to the anatomical cross-section. Since Huber has shown that muscle fibers in a single fasciculus of a given muscle vary greatly in length, in some fasciculi from 9 mm to 30.4 mm, it is unlikely that the physiological cross-section will pass through all the fibers. Estimates have been made of the strength of muscles, and it is probable that coarse fibred muscles are somewhat stronger per square centimeter of physiological cross-section than are the fine fibred muscles. Fick estimates the average strength as about 10 kilograms per square centimeter. This is known as the absolute muscle strength. The total strength of a muscle would be equal to the number of square centimeters in its physiological cross-section times 10 kilograms. The work accomplished by muscles. For practical uses, this should be expressed in kilogram meters. In order to reckon the amount of work which a muscle can perform under the most favorable conditions, it is necessary to know 1. Its physiological cross-section, 2. The maximum shortening, and 3. The position of the joint when the latter is obtained. Work equals lifted weight times height through which the weight is lifted, or work equals tension times distance. Tension equals physiological cross-section times absolute muscle strength. If a muscle has a physiological cross-section of 5 square centimeters, its tension strength equals 5 times 10, or 50 kilograms. If it shortens 5 centimeters, the work equals 50 times .05 equals 2.5 kilogram meters. If one determines then the physiological cross-section and multiplies the absolute muscle strength, 10 kilograms, by this, the amount of tension is easily obtained. Then one must determine only the amount of shortening of the muscle for any particular position of the joint, in order to determine the amount of work the muscle can do, since work equals tension times distance. The tension of a muscle is, however, not constant during the course of contraction, but is continually decreasing during contraction. It is at a maximum at the beginning and gradually decreases. This can be illustrated by the work diagram. AMD ordinate equals tension. AVX abscissa equals shortening. AD equals tension of muscle in extended or antagonistic position. AV equals amount of actual shortening. AM equals tension in mid-position equals absolute muscle strength. dV shows how the tension sinks from maximum in the extended position of the muscle, where it is about double that in the mid-position, M, to nothing on complete contraction. Delta AdV equals work diagram. In reality, the hypotenuse is not straight, but has a concave curve. The delta has the same area as the rectangle AMM'(V). AM equals the average tension. Work equals AM times AV kilogram meters, if the size of the ordinate is expressed in kilograms and the abscissa in meters. Although the muscle works with a changing tension, yet the accomplishment is the same as if it were contracting with the tension of the mid-position. In reality, the amount of work is somewhat greater, since even in extreme contraction the muscle still retains a certain amount of tension, so that the maximum amount of work is more nearly like AdX. We know that a muscle may have an extreme actual shortening of about 80% of its length when the tendon of insertion is cut. The trapezoid ADSV represents more nearly the amount of work, but since there are only approximate values and ADSV is not much larger than AM'V, we may use the latter. Only the tension and amount of shortening are needed to determine the amount of work of the muscle. Neither the lever arm nor the fiber angle in pinnate muscles need be considered. The diagram shows that the lever arm is of no importance for determining the amount of work the muscle performs. JB and JB1 equals 2 bones jointed at J. CD and EF equal the direction of the pull of 2 muscles of equal cross-section, each having a muscle tension of 1,000 grams. The centers of the attachments are such that perpendiculars J c and J